Hello class, this is a video tutorial on exponential models. Real-world scenarios such as population growth or radioactive decay can be modeled as an exponential function. So we call it exponential growth when a to the power of x, we have a positive x, and it's an exponential decay when we have a negative x. However, these models and all the nonlinear models that we'll see in the coming topic have certain limitations, as they do not take into account other real-world factors such as time cannot be negative, and so can't accurately model negative x values, and you'll see what we mean in a moment. Time cannot run indefinitely. Models assume it will always represent the scenario, but it doesn't take into account, say, if in the example that we're going to see, it's this population growth of fish in a pond. It doesn't take into account whether or not there's a tsunami or something that eradicates them. And lastly, models representing populations cannot assume the continuous growth of the population. So again, in this example, you'll see that the fish can't always keep growing, that it eventually has to stop at some certain point. So here we go. First, in order to model what we're seeing, we need to understand what we are graphing. So before, it was y equals a to the power of x. Now, instead of y, we are saying it is now going to be n for the number of fish, 500 times 1.5, and that's our value of a, to the power of t. Notice how this represents very closely what we had previously seen. So, I want you to go ahead, pause the video, and fill out these values here, and then graph them yourselves. So I'm going to do that now. Here we go. How you type this in is going to be 500 bracket 1.5 to the power of 0. That gives us 500. We'll delete the 0, place in 1, gives us 750 to the power of 2, 1125 to the power of 3. Okay, so now that we're getting incomplete numbers, we should either round up or round down to the nearest whole number, because you cannot have 0.5 of a fish. So 168. Rounding up to the nearest whole number to the power of 4, 2531, rounding down to the nearest whole number. Now that we have these values, we can graph them ourselves. So here we go. 0, 500. 1, 750. That would be here. 2, 1125. 1125. So this is 250. It's exactly here. 1688. Line. You can use a ruler for this one. This is 1750. 1060. Oops. 68, I believe. So this line here would be 16125. 1625. 88 would be slightly above that one. So let's just place it somewhere along that line here. And lastly, 2, 5, 2, 5, 3, 1. This is 2, 5, slightly above this one here. Joining the dots. Again, remember to make this as smooth of a line as you possibly can. Drawing an arrow off into infinity. Now, of course, I was a little bit more properly prepared. I've actually prepared a proper one down here. So I'm going to be using and referring to this one instead. But yours should look somewhat like this. So now using either the table of values or the graph, we can estimate or find the exact values of these questions here. So how many fish are present after 2 years? So if we're only given the graph, you're going to go to the t for the number of years, find the number 2, and graph it along to that point there. So 1,125, which is what is shown here. So this is 1125 fish. At 5 years, now notice how we don't have 5 years in our graph here. If we only were given the graph, we would go along to here, find that point of intersection, like so, and use our ruler to see how many there are there. Slightly above 3,750. Let's say that's about approximately 3,800. So approximately 3,800. We could, of course, if we've been given the formula, we could just substitute t is equal to 5 to find the exact value, which is what I'll demonstrate here. So this number is taken from the graph, but since we have the equation, we can just substitute that value there, and there we have it. So it's actually exactly 3,797, rounding up to the nearest whole. So we weren't too far off in that one. And the last question that we have here, 18 months. Now remember, t is representing the value in years. So if we were to do 18 months, the common mistake is to keep going along the graph until we get to 18, but that does not represent 18 months. 18 months in years, you can always just do this, 18 divided by 12. It's 1.5 years. So for this, you could, on the graph, find 1.5. In this case, it would be here. Finding that point of intersection with the graph. Moving it along there. And that one there, I'd say is about close to 900 fish. So we can approximate using the graph. So approximately 900. But of course, because we're given the actual formula for the fish, we can just find the exact value here. So 1.5 to the power of 1.5. So 919 exactly. This is 900. So this is from the graph. This is from the equation. So depending on what tools we've been given, we can either just approximate using the graph or just use the equation itself. how many fish were born since the first observation until 4 years. So what this question is asking us is, since we first observed the pond until the 4th year, how many fish were born in that time? Well, in the 4th year, there were 2,531 fish. And if we subtract the original amount, the difference tells us the exact number that were born in that time. So this is actually 2,031 fish. And lastly, as we discussed earlier in the video, what limitations might this model have? Okay, so the first limitation is that t equals time in years. So we cannot use values of t is less than 0. Also, the model assumes the population, or the fish population, will always grow at the same rate every year forever. Okay, so this model doesn't stop at any given time, and it assumes that the rate of growth between 2 and 3 years will be the same from 3 to 4 years. But you don't know whether or not a storm hits, or if the pond gets, I don't know, polluted or something. So it's always just assuming it has the same growth rate every single year, and that it will always be growing. So, there's actually more points of discussion that we can have there, but these are just a few that I can come up with right about now. So I hope that gave you an insight to one example of an exponential model. Hope to see you in the next example.